X-ray tubes are used for a variety of medical and testing purposes. While there are several designs in use, they all produce X-rays through the same basic mechanism. An X-ray tube consists of an outer evacuated glass envelope that contains two essential items, the cathode emitter and the anode target. A large potential difference of typically 100,000 volts is maintained between the anode and the cathode. The cathode emitter is a piece of metal that is heated by a low voltage supply. Electrons are liberated at the cathode by thermionic emission and are accelerated in the electric field between the anode and the cathode towards the target. The cathode is shaped to focus the electrons onto a small portion of the target, which increases the intensity of the X-rays produced. The target is typically a piece of tungsten or molybdenum, which may be embedded in a stationary water or oil-cooled rod, or on a rotating disc. The high-speed electrons collide with the target and rapidly lose energy. There are two X-ray producing interactions between the incident electrons and the atoms in the target. In the first, electrons are scattered by electrostatic interaction with the nuclei of the target material. This results in the direct emission of X-rays from the electron as it loses energy. This process is called Bremsstrahlung, from the German meaning braking radiation. Bremsstrahlung radiation has a continuous spectrum corresponding to electrons losing different fractions of their initial kinetic energy. When the electron loses a small amount of energy, a long wavelength X-ray is produced. When it loses a larger amount of energy, shorter wavelength X-rays are produced. The spectrum has a minimum wavelength below which X-rays are not produced. This corresponds to the highest energy X-rays which are produced when the electron loses all its kinetic energy. The second interaction that can take place in the target is between the incoming electrons and the electrons of the target atoms. If the incident electron has certain characteristic energies, it can eject electrons from the inner shells of the target atoms. These are filled when outer shell electrons make transitions to fill in the inner shell vacancies. These transitions reduce the energy state of the atom by emitting X-rays with characteristic wavelengths. These characteristic spikes are superimposed on the continuous Bremsstrahlung spectrum to give the X-ray spectrum observed by experiment. If we change this plot to show the number of X-ray photons versus photon energy, we see that the basic shape is reversed with a continuum that rises from low energy to a peak, then falls to zero at the point where the maximum X-ray energy is achieved. The characteristic spikes due to target atom inner shell interactions are also still evident. If the potential difference between the anode and cathode is increased, the electrons will gain more energy prior to collision with the target, and both the height of the peaks and the highest possible energy of the X-rays will increase. The target anode is angled to ensure that the X-rays are directed through a window in the desired direction.